Hi, I'm Princess Senate, conference producer for Technology Networks, and I am here to introduce our next talk, Untargeted Analysis Using Different MS Platforms. I am pleased to welcome our speaker, Brian Quinn. Brian has more than 30 years of experience in agrochemicals, pharmaceuticals, veterinary drugs, and environmental contaminants. He focused on agrochemical research for the first decade, then explored endocrine disruptors, chemical ecology, medical device manufacturing, and food security at Queen's University, Belfast. Brian has authored numerous publications and collaborated successfully with industry universities and governments on various projects. A warm welcome to you, Brian. Following the presentation, we will have a Q&A session, and we welcome any questions that you may have. Please ask questions using the Q&A system to the right-hand side of the video player. You can also use this feature to connect with attendees and discuss the talk. So feel free to take advantage of the chat system by introducing yourself and sharing your thoughts during this presentation. You can also benefit from some fantastic supporting literature from which you can download for free below the video player. If you experience any technical difficulties during the presentation, please request help using the technical help icon in the menu on the left-hand side of the player. I will now hand over to Brian to begin their presentation.
Thank you so much for the introduction. Basically, we look at targeted and untargeted workflows for food analysis. There's a big difference between the two, and I'd like to basically show you what the differences are. And in this talk, I'm going to mainly work on untargeted. So it's important that you see the differences. So we're going to start with targeted here. So what is targeted mass spectrometry? It means we know the analyte that we want to detect and quantify. So normally we have a parent and daughter ions that are input into an MRM, which is a multiple reaction monitoring retention time window to better increase sensitivity. So here's an example. Zearalenone is one of the 10 regulated mycotoxins that is found especially in corn. What we do is we find that the parent ion is 317 when it's in negative mode, and the daughter ions are 175 and 131. So we analyze the standard to get a retention time, and then we build a safe retention time window, which means we buffer it by 0.1 to 0.2 minutes on both sides to make sure that we catch the molecule as it runs through the column. We also perform source optimization to decrease the limit of quantitation. That's one of the most important things about using targeted MS, and especially we use triple quad mass specs to do this because they're very stable platforms. And what we do is for quantitation and confirmation, we use the daughter ions and not the parent ion. So the advantages to targeted MS are excellent quantitation and lower LOQs. And the LOQs are lower, A, because the triple quad is a very stable instrument, and B, we are optimizing the source for each compound as it goes through. And we can get targeted methods of up to 400 or 500 compounds per method, which is great because their detection limits are a lot lower than high resolution mass spec that we would use for untargeted work. So how do we use untargeted MS in food analyses? Mostly food contaminants. We look at nutrients, vitamins are a big thing, and antioxidants, and any other compound that you want to look at in a commodity. It's important that we have full profiles of all these commodities that we eat because we want to know how our nutrition is and to make sure that our food's uncontaminated. So common feed and food contaminants, because I will also work on animal feeds, are pesticides, mycotoxins, veterinary drugs, plant toxins, and PFAS. PFAS, are the forever chemicals that everyone's talking about. And as you can see, the one depicted here, there's a lot of fluorines on this compound, and it is a forever compound. It'll take hundreds of years for that to break down. And now we're finding it in almost every food commodity. So now I want to move on to untargeted mass spec because it's an emerging field, especially for food, and we are one of the leaders in food omics in our group at Queen's University, Belfast. We do a lot of work on untargeted MS to show the country of origin of a commodity, and also to look at contamination of a commodity. So what we do with untargeted MS is we look at compound or elemental footprints in samples. That footprint or fingerprint is really important for us to tell differences amongst samples. say I'm going to be looking at corn. I'm going to test the world's corn, and I want to know where it's grown. What we do is we extract it and we look for either chemical or elemental footprints to see what the pattern looks like, and then we see the differences amongst samples from each country. So metabolomics and elementomics are the most common types of untargeted analysis. And what I described earlier with the corn is exactly metabolomics. Metabolomics is using liquid chromatography, high-res mass spec, and also gas chromatography mass spectrometry. Elementomics uses what we call ICP mass spectrometry, which is inductively coupled plasma, and that's how we look at multiple elements at one time. The other thing that we do with untargeted mass spec analysis is screening studies. And at the end of this program, I will show you a very interesting screening study that I've been working on for the last 2 years. So let's first look at metabolomics, elementomics. We use a three-pronged approach in our lab because we have the instrumentation to do so. So what we do is we run 10 to 15% of our sample sets on 3 different platforms. ICP-MS, again, that shows elements, GC-MS, that shows volatile compounds, and LC-QTOF, which shows extractable compounds. So using these 3, basically we cover every known entity or a known component of each commodity we're looking at. And basically after these 10 or 15% of these samples are run, we've modeled the data and we see which of these platforms produces the best model, and that's what we use for the rest of the project. So again, ICP-MS, elemental, GC-MS, volatile, and LC-QTOF, extractable footprints. So system suitability tests are run on each platform to make sure they were ready for the main sample set. This means that we'll run QC samples and blanks to make sure that the systems are stable, because as soon as we start, we don't want anything to change. The most important part about metabolomics and elementomics are every sample is run exactly the same. If we don't do that, then we can get variability in our studies. And variability is a killer for these sorts of studies. So certified reference materials. This is the most important part of your metabolome or your elementome, is the certified reference material. We have to have these in there because it shows how your instrument and how your extractions run day to day. So right now, one of the things that I'm working on is mapping the world's soya, because we're trying to eliminate soya coming into the marketplace from Brazil, where they've been burning the rainforest over the last few years in order to make land for soya. And what we have to do is make sure that we have a CRM for soya, which we were able to buy commercially. And this shows us after over 2 years how our instrument functions and also how our extraction works. So if you can't find a CRM in a commercial entity, you can actually make your own CRM. Say you want to work on pomegranates and you get pomegranates from 10 different countries. What you do is you combine those, all 10 countries, and you mix them after grinding for 90 minutes, and then you evaluate your model. You extract the CRMs and you put them in your model to make sure that they're separated from all the other country groups. We've done this many times, because especially like soya, for if we can't find it commercially, we have to make it ourselves. Okay, let's talk about the first platform, which is GCMS, MS, and MS, or GC-TOF. So right now our lab only has an MS. Metabolomics is much better done on a TOF, but we can get around it using some methods I'll show you later. So basically, it's a very simple method. We weigh a sample, whatever it is, into a volatile organic analysis file, randomize them, which randomization is very, very important, because if you have any temporal differences at the time of your run, your run is maybe 10 hours long, instruments aren't completely stable. You have to make sure you randomize the different countries, because what we do is we use 7 to 10 replicates for each country. And we want to make sure that the samples are randomized on the auto sampler, because any temporal differences are then taken into account in your models. So we analyze these samples using solid phase microextraction, which is just a little bitty fiber that is pushed down into the sample while it's being heated up in a small oven. And then what we do is we have a linear temperature gradient on the GC. It's very important to keep these gradients very simple so they can be reproducible over years and years of work, because some of these metabolomic studies will go on for 3 or 4 years. And what we do for the GC-MS is we run the sample through both the MS and the TOF for unknowns analysis. So the data workflow for GC-MS is what we do is we run the unknowns analysis, and then we select compounds in there that score 80% or better. Now, what we do then is use the NIST library, which is a library that shows the spectra of the compounds that we chose, and we can determine basically by that library the differences amongst the samples. So say you had samples from 5 different countries and they were rice. We can look at this list of compounds from the unknowns analysis and the NIST library, and we can figure out the differences of the compounds amongst the 5 countries. Now, the metabolomics data workflow for GC-TOF is a little bit different, because that's completely untargeted, the TOF, whereas we have a bit more targeted with the MS and the NIST library. So again, we run it through the unknowns analysis, and what this does is this deconvolutes the data. Then we move from there to Agilent ProFinder, which is a software for the Agilent GC and other Agilent platforms. And what we do is we produce a chef file. And from this chef file, we move this to Mass Profiler Pro, and we build an unsupervised model. So unsupervised models are where we start with any metabolomic or elementomic modeling. We have to have that, and we have to show separation in the unsupervised model before we start building supervised models. This is extremely important. I review many papers in this field and constantly see that the unsupervised PCA models are just not where they should be. And the study should have never actually even gone past that point, because supervised models are designed to show separation. So again, unsupervised models must show separation before you move on with any metabolomic or elementomic study. Now we're going to move to ICP-MS. And we've used this very successfully for 2 or 3 commodities in the last couple of years. So it's, again, a very simple method. With elementomics and metabolomics, we keep the methods simple. The more steps you have in an analytical method, the more compounds you lose. And the goal here is to get as many compounds or elements in your metabolome or elementome to show differences amongst the samples from different countries. So basically, we weigh usually 100 milligrams into a 50 mil plastic conical tube. We call them Falcon tubes. We add 2 mils of concentrated nitric acid and 2 mils of hydrogen peroxide to each sample. We allow them to digest in the hood overnight. We then microwave the sample the next day for about an hour and a half to complete the digestion. We dilute the sample to 20 grams using a weak hydrochloric acid solution, because we need to keep it acidified. For elements, they have to be acidified as you introduce them into the ICP-MS in order for them to freely flow and to also ionize, or basically get into the plasma, because ICP-MS uses a 6,000 to 8,000 degree Celsius argon plasma, and that's how the compounds and matrix are pushed through the instrument. So again, we randomize the samples from each of the countries and the CRMs and the blanks on the autosampler. Again, it's very important for CRMs and blanks to be run with every sample. If these QCs aren't there, you could have some serious issues with your data. Now, the data workflow for ICP-MS is actually quite simple, and it's very different from GC-MS and QTOF, because we quantify the elemental data using external standard curves. So we run standard curves and blanks before we even put in any of the external samples on, because it's important that we get concentration data, because that's how we tell which compounds are which elements are important in the separation amongst countries and in each commodity. Now, because you can get massive differences, 3, 4, 6 orders of magnitude between the concentrations of trace elements versus macro elements, we do a log-based 10 or univariate scaling transformation to the data. That tightens it up, and that allows us to do a much better modeling. And for this, we use our unsupervised models, PCA. which is principal component analysis, and we're using Simco, which is a software that's very common for this sort of work. And again, if we see separation in the PCA model, then we build other supervised models like PLSDA, which is a linear supervised model, very commonly used in our field. Now, the third instrument that we use is an LC-QTOF, which is a high-resolution liquid chromatography instrument. And what we do with all of our LC work and all of our GC work, if it's not volatile, is dilute and shoot. Dilute and shoot, we adopted in our lab about 3 or 4 years ago when we wrote a review paper on it, because we wanted to show our colleagues that, using costly and basically sometimes limiting cleanup steps like solid phase extraction can reduce the number of compounds that you get in your metabolome by a tremendous amount. Yes, it's cleaner for the instrument and you have to do less maintenance on the instrument, but you can lose a lot of the features that you want for this metabolome. So we do dilute and shoot. And dilute and shoot basically is we extract the commodity, we centrifuge the commodity, and we filter it. And right after that, we analyze it. So before we do this, we do range finding tests. And for extraction, we use various solvent mixtures or water mixtures. And we start at 100% solvent and we go all the way down in 10% increments to 100% water. What this does is we basically make sure that we get the largest number of features in our extracts. So after we do that, we also look at the final extraction volume, because the last thing we want to do is saturate our detector. So we use 3 or 4 final extraction volumes, usually like 2, 3, and 4 mils. And then what we do is we shoot them on the detector. And what we're really shooting for is about 80% of the detector. If we can get it in that sweet spot, we know that we can see compounds that are in low concentration, and also stuff that's really high concentration in the same metabolome. Again, the goal here is to make sure we get as many features in our metabolome so we can tell the differences amongst country or other groups. Now, we use solvent gradients that are simple, and we use solvents that are simple. I normally use acetonitrile with 0.1% formic acid with water that also has 0.1% formic acid. I don't see any reason to use complicated solvent gradients and complicated mixtures of solvents, because we're really trying to just easily separate in a 20-minute run, which is what we use. We're trying to separate these compounds out to show the features. We also use columns that are known to retain polar molecules to increase the number of features. Not every compound is going to retain on every column. I mean, because there's sometimes tens of thousands of compounds in each one of these extracts. So what we do is we use, Agilent has an SBC18 pour show we use quite frequently. And Waters has a wonderful compound, or a wonderful column that's called a T3, which is the industry standard for retaining polar molecules. So these would be the two we would use the most. And they're very easily sourced from both of those companies. Again, we randomize all of our samples on the auto sampler because it's so important to do this. Columns can get, active sites can get blocked, things like that. And again, this is why we have these QC parameters, in order to make sure that we don't skew our data in any direction. Now, one of the most important things about metabolomics using an LC-QTOF is we keep our capillary and fragmenter voltages low. We do not want fragments, because fragments can just convolute the situation. Sometimes we're looking at 6, 8, 10,000 compounds for a metabolome, and to have fragments for each one of those would make it very, very difficult to analyze. So keep those fragmenter and capillary voltages low. We want parent molecules, not fragments. Now, the data flow for LC-QTOF for the Agilent, what we do is we run sample data through Agilent ProFinder, which is their software. We export the chef file, just like we did with the GC-QTOF, into Agilent Mass Profiler Pro to produce an unsupervised model. And if the PCA unsupervised model shows separation, then we start building the supervised models. There are other ways to extract data from high res, like QTOFs, and they're called mass binning. And what we do is we bin the masses from the entire output into 0.5 Dalton or larger Dalton windows. So we make a window that are half Daltons each, and from there we can also model that using Simca. So it depends. You have choices. You don't have to use the software that's provided with the instrument if you're not comfortable doing that. You can use a software that you already know. Unsupervised models. Again, I said previously that I do a lot of reviews for food journals and other journals like metabolomics, food chemistry, and I see a lot of these errors that people make, especially with your PCA model, your principal component analysis. If you have no separation, what you're doing is over. You need to change your parameters to try and get separation in your PCA. But if you have no separation, then basically you need to go on to a different project or change what you're doing. This is I can't emphasize this enough. And again, if you're publishing this field, please add the PCA plot to your manuscript. So as a reviewer, I can see if you have separation or not. Here's an example PCA plot. This is a PCA of soya from many different countries. And you can see some separation amongst countries, and we know what that is because of our QC parameters. But as you can see, we have general good separation amongst the groups. And again, you see the CRMs in there. That's the most important thing. If those CRMs don't clump together, or they are over another spot in the metabolome, then you need to change what you're doing with CRMs. Now, supervised models. Once you finish your PCA, you're going to run supervised models. And supervised models are designed to separate metabolomic and elementomic groups. Again, if you only show me a supervised model in your manuscript, I'm going to reject it until I see the PCA. So there are many types of supervised models, like linear models, which are one of the most commonly used, PLSDA, OPLSDA, and LDA. And then there's also machine learning models like support vector machine and random forest. There are many, many other models, k-nearest neighbors, and there's new models coming out, usually every few years. So these models are very, very constantly used in our field. So they have a very good track record for being robust, and for basically, if you put your samples in these models and you show that you have separation, you've got good data. So we also try every possible model we can with different scalings like Pareto, univariate. There's a lot of different scalings you can do in order to determine which combination provides the best separation in your model. So don't be afraid to try everything. And right now we're working with the Queen's University computer gurus, and we're trying to automatically model all of our data on all of these model platforms as soon as we produce it. So, and half the time, or sometimes more than half the time, we spend in the laboratory and in the office is modeling data, because the data sets are so large that it takes a long period of time. So right now we're working with this group at Queen's University to try and do automatic modeling of our data, and that's going to save us a lot of time in the future. Now, here's an example of an OPLSDA plot, which is a linear plot. Now, what I want to show you here is there are some outliers on here, and you do not remove outliers unless there's a good reason, like you had an instrument failure, or that your extraction was bad. And if you do remove them, you must repeat your analysis and add those in. I've had recent papers where people are they're actually removing outliers in their model to make it a better fit, and that's just really bad science. We need to make sure that, with all the warts, your data is what it is. But we consider this to be a pretty decent OPLSDA plot. I will put the caveat in that this OPLSDA plot is linear, and linear models need to be balanced, which means you have the same or similar number of samples in each group. And right now we don't. So the model is going to be skewed a little bit towards the countries like China and Argentina that have less samples in there. But this is what a good OPLSDA plot looks like. And sometimes the separation can be even much better. But we're very happy with this model and this work. This soya work has been going on for 2 years. We've collected hundreds of samples from many different countries. And right now, using this, we can tell the world's soya production, the country of origin, with a 97.5% confidence. And as we do more and more samples and add them to our models, that number is only going to increase. This, I will tell you, is one of the most important things, because a lot of feed companies and livestock companies and grocery stores with the likes of Tesco and Sainsbury's want to know where their soya is being produced. They do not want to support soya that's been produced in a recently deforested area in Brazil. So again, this is one of the examples of having a really, really great data set it's gonna help the environment, hopefully, and it's gonna help businesses and consumers know where their soya comes from. Now, quality control for metabolomic and elementomic models is absolutely key. Again, when I review papers, manuscripts from great journals, sometimes I see a complete lack of QC. So first of all, I talked about CRMs. If you don't have CRMs, you're going to be in trouble, because you don't know day to day what your instrument and extraction variability is. The other thing about models is they become overfit quite easily. And some people love the look of an overfit model because the separations are almost perfect. But an overfit model means that they're going to work on the data set from which they were built and not work well for external samples. So the goal of a model like the soya when we're working is that somebody's going to send me samples from whatever country it is, and we're going to be able to tell, if, what country it's from, if we have that country in our model, or we can say it's from somewhere else. But if our model is overfit, we're not going to be able to work with external samples. So we use both internal and external validations to make sure our models are not overfit or skewed in a certain direction. So it's all important. It's also important to understand requirements for supervised models. And as I said before, linear models need to be balanced, which means each group needs to have the same or very similar a number of samples in that group. I can't say that enough, where I see, a paper that has 15 samples from somewhere and 200 samples from the other. And that's going to skew that model to a point to where it's just not usable. And again, never, ever remove outliers in a model unless there's a very good reason, like instrument failure or extraction failure. External validation. So the most common external validation is is by using 70% of our samples to build the model, and then test it with 30% of the samples. So basically, you want to make sure that those 30% that are external validation samples are correctly classified from the model you built with the 70%. Now, the 70-30% isn't set in stone. Some people like the 2/3, 1/3, and some people for 80-20. It really doesn't matter as long as you do the external validation. That's the most important thing. If it's not there, I'm going to be the first to ask why it isn't, and if you can do that in order to make your manuscript or your work to be publishable. Internal validation, also very important, especially to prevent models from being overfit. Good data and permutation tests are the most important tools. We use n = 50 permutations to make sure, normally we can do more in order to make sure that our models are not overfit. And the second really important thing we do is an internal validation, which is called leave 20% out. So 20% of the samples are left out and are used to test the fit of the model. This is repeated 5 times to make sure that all 100% of the samples have been a part of that 20% internal validation. Now, both the external and internal and the CRMs are the 3 most important things you'll do if you ever work with metabolomics or elementomics. And I have to say, I was just at the American Society for Mass Spectrometry meeting in Houston, Texas, a couple weeks ago to give a talk about the soya work that we're doing. And they, the people that are doing human metabolomics have now moved us over, and now we're called foodomics. So we're actually a different group of metabolomics or elementomics. So the summary for metabolomics and elementomics is the extraction column, extraction solvent, analytical column, and final volume are extremely important to LC-QTOF because those parameters will define the number of features you find. CRMs are the most important samples you analyze because they show if your extraction and instrumental analyses are consistent. PCA plots must show separation before continuing with supervised models. And these model QC steps like internal and external validation are key to producing sound data. So commodities we have recently analyzed, soya. We're working on black pepper right now. We published in a basmati rice paper in food chemistry it's been a year and a half ago. We're working on ginger because it's one of the most difficult ones to separate out amongst countries, at least dried ginger. Fresh ginger is easy. And then leeks. We had a study a couple of years ago that we published that we could tell the difference between organic and conventionally grown leeks. So these metabolomic and elementomic studies have some great power to them if they are used correctly, built correctly, and validated correctly. Okay, now I'm going to move on to something called untargeted screening. This is one of the more new type of untargeted workflows for especially LCMS and GCMS. You know, sometimes we'll get a sample and we have no idea what's in the sample. Somebody just will say, you know, I think there's something in here that I want to look at. And so what we do is we do dilute and shoot, which I'll show you the same protocol later. And what we do is we can monitor thousands of compounds in a single analysis. You know, and we do this with good database software. You know, and right now we're working with Agilent and have been for two years on untargeted screening projects, and they just put out some new database software that has made analysis, which used to be 45 minutes, down to 2 minutes for analysis for 14,600 compounds. Which, you know, this work that we're producing is designed to go into contract labs to do screening of animal feeds. So again, we use dilute and shoot workflows because the last thing we want to do is lose any compounds that are in the extract. So no cleanup, no liquid cleanup. We do liquid solid or liquid only if it's a liquid sample, and then we just extract, centrifuge, and filter, just like metabolomics. Now, before the main analysis, we also do the solvent water mixtures for each commodity to make sure that we're pulling out as many compounds as possible, you know, not just for the features, but also to make sure we get all the contaminants. And again, the final extraction volume is optimized to make sure we're not saturating the detector. Saturating the detector is a very bad thing because you can't trust the analysis in any mass spec once you've saturated the detector, especially QTOF. So you have to make sure that your extract is not too concentrated for the instrument that you're working on. Now, again, we use solvent gradients that can be reproduced easily. And again, I use acetonitrile or methanol with 0.1% formic acid, and also water with 0.1% formic acid. You know, methanol I tend to avoid because you get higher back pressure in an instrument. You know, it's not as compressible as acetonitrile, but they both have very similar, almost the same allotropic strength. So, you know, just because I use acetonitrile doesn't mean that you can't use methanol, but you still keep it simple because you want it to be reproducible. And again, we use columns that are known to retain polar molecules, the Agilent SBC18 porous shell and the Waters T3, because we need to increase the number of features or compounds that we are, extracting from whatever matrix we're working on. You know, it's very important that that we get the maximum number of compounds out of the commodity because we need to know what that contaminant is. You know, and this is not as important as the metabolomics, but we also randomize samples and QC samples on the auto sampler to make sure that our matrix has not somehow had some issue with making the mass spec or the column dirty. Now, one of the most important things for untargeted screening is that we raise our capillary and fragmenter voltages. So you can't raise them so high that you're blowing molecules to bits, but you have to raise them to where you get fragments because you want both parent and fragment ions to help make matches for the database. The database is not worth as much if you only have parent ions. Those fragments are so important. So make sure you raise your cap voltage and your fragmenter voltage when you're doing this sort of analysis. Now, the database is extremely important, and you have to make constraints on that database, because the last thing you want to do is report a false positive. If you got some company you're working with and you tell them that you have some sort of contaminant, and it's not really there because you didn't have good restrictions on your database requirements, then you're going to cause them some problems. So what I work with is parent ion within 5 ppm. That tolerance I'll allow for there. I also do 5 ppm for the fragment ions, but I'll actually loosen that to 10 ppm because, we're running many hundreds or thousands of compounds in every run in 20 minutes. And sometimes the fragments will go a little bit further out, and that's really acceptable. But 5 ppm is what I start with because you want to keep it as strict as possible. Now, we also want a minimum match to the database you're working with 80%. I've seen people go down to 70% and lower than that, reporting screening data, and I just don't think that it's robust enough. I think we need to keep it above 80% because it's important that your data is that it shows that you have a good database match. It's just really important that your requirements are robust. Retention time matching. This database I work with has 14,600 compounds. I can't shoot every compound onto the instrument, but I put about 700 on there. And what we do is we report the retention times, and so the other compounds should match with similar compounds of the same class. Like, if you're working with azoxystrobin, the other strobin, which is a fungicide, the other strobins should be of a similar retention time. Now, it's very important that the parent and fragment ions have the same retention time. If the fragment ion has somehow drifted away from the parent ion, then it's not a match, because it very well could be something else. And at least 2 fragment ions must be present for each parent ion. If you don't have 2 qualified fragments, then it's not a match in my view. So very important, those database requirements are there. So right now, I've been working with animal feed. There was an issue in Ireland, well, actually in France, with Irish racehorses, that they had been fed a compound called zolpadorol, which is a beta agonist that's completely legal in the United States and South Africa, but not legal in the EU, China, and most of the rest of the world. And what happened was this zolpadorol is used to thicken the muscle fibers. You would give it in American cattle about 7 weeks before slaughter because it raises their muscle mass. But it's a performance enhancer in racehorses. And so this was found in those racehorses, and it took a couple of years, but it was found in molasses that had been given to the racehorses. And this is what spurred this work on. Right now we're running porcine, equine, ruminant, and poultry feeds for 14,600 compounds in a 20-minute run. A year ago, it took me 45 minutes to analyze this 20-minute run, and now we can do it in 2 minutes with new software from Agilent. We've had very successful spiking studies and are moving towards method validation. So this is another extremely powerful tool that is an untargeted workflow. And I think that as the years go on in the next 5-10 years, you're going to see a lot more untargeted work out there. I know that we have 4 or 5 more workflows that are in progress right now with different researchers, because this is the newest thing that's really going to make a difference, especially when, you're trying to analyze for 14,600 compounds in 20 minutes. You're not going to do that with a targeted workflow. So in targeted feed screening, again, the extraction steps and analytical parameters are much like metabolomic studies, except for the capillary and fragmentar voltages, because those need to be raised. Metabolomic studies, voltages are low because we want no fragmentation. For untargeted screening workflows, we raise the voltages because fragments are a database requirement match. And the database requirements must be strict to reduce false positives. So our summary basically, it says, basically I'm saying is define your objectives when you're evaluating your workflows to better decide targeted versus untargeted workflows, and ensure QC steps are embedded in your workflows to produce more competent and more reliable data. QC is where it's at, internal standards, surrogate standards, CRMs, All of these QC steps with the models we take, they're extremely important. You can't do enough for this in order to make sure that your data, especially analyzing food that people eat and food that people rely on to be healthy and free of contaminants. Your job is really important to make sure that our food supply chains and the food we get in that grocery store is safe for consumption. And that's it. Thank you.
Thank you very much, Brian, for sharing your expertise in the field. We will now move on to the Q&A session. And the first question I have for you is, what is untargeted analysis?
Well, I explained untargeted analysis in the presentation, but basically is you're given a sample that you don't know what's in there, and so you have to change your workflow in order to look for many different compounds. Untargeted is mostly done on high resolution instruments like QTOFs, Orbitraps, both LC and GC. But there's a new field coming out that's doing targeted screening also. And it's just that you have to input many different MRM windows, of basically your parent to daughter ions to do that. But again, mostly high res instruments, and you change your workflows depending on if you're doing metabolomics or screening.
Thank you, Brian. Moving on to your next question, how do you define metabolomic parameters in study designs?
Okay, we define our parameters by first extracting the compounds, and LC-QTOF, we look at the number of features, and then we separate it using ProFinder in Agilent or mass binning and SIMCA. For the ICP-MS, what we do is we look at each element that we analyze, we quantitate it, and we look at what we call VIP scores there, which basically tell us which elements are responsible for the differences amongst the different country groups or different groups that you're analyzing. And for GC MS, we actually use the NIST database to tell the difference amongst compounds, and GC QTOF is just like LC QTOF, where we'd use first the unknowns analysis, then ProFinder, and then Mass ProFinder Pro, in order to tell what the differences those parameters that show what compounds or what elements are causing the difference amongst your samples, your groups.
Thank you, Brian. You've just touched on the MS parameters. So this question ties in nicely with that. What MS parameters are different between metabolomics and screening workflows?
Well, the main difference, as I've pointed out in the presentation, is for LC-QTOF is going to be your fragmenter and your capillary voltage. We must keep the voltage low to reduce or try and keep any fragments out for metabolomic studies. For screening studies, untargeted screening studies, we must have the fragmenter and capillary voltage higher so we can have fragments to do database matches.
Thank you, Brian. We do have some time left for one final question, which is why use dilute and shoot versus SPE against quechers?
Catchers.
Catchers.
Yeah, no, it's so SPE and catchers is a very specialized method that was developed by Steve Lahote at the USDA many years ago, and it basically tries to remove the matrix. When we do dilute and shoot, we don't care about the matrix. We know we're going to have to do more maintenance on the instrument, but what we're worried about is losing compounds. Every analytical step you take, whether it's an extraction, whether it is a cleanup step like solid phase extraction or catchers, everything you lose compounds. And in order for untargeted screening and metabolomics and elementomics, we need to make sure that everything possible is in that sample is in there. So we have fully adopted dilute and shoot for both untargeted and also our targeted work. So
thank you so much, Brian. Unfortunately, that's all we have time for today. Any questions that we didn't have time to get to will be sent to the speaker after the event. While you're here, don't forget to check out all of the free to download literature and resources available below the live stream player. And as with all the other talks in the event, this talk will now be available to view whenever you want for the next 30 days. That just leaves me to say thanks again to Brian for his excellent talk. And for everyone watching, we will be back soon with the next talk.